I'm Tomáš Kuzin, and today I'm going to present you something about the sensor fault detection techniques. So today I'm going to present you some basic nowadays used techniques, how you can detect suspicious values measured by sensors, which may show you that the sensor might break down, or on the other hand, it also may show you some interesting measurements which both are in your field of interest. So first, I looked at the most often and good modelable errors, which are when you have sensors. So first is that the sensor gives a constant value, which means that it's probably frozen for a while, and important is that the value has no relation between the state of observed physical phenomena and the measured value it returns. Another typical is a short value, for which it's a short error, for which it is typical that for a short period of time the sensor shows rapidly different values. It might be caused by short circuit in a circuit, or some interference, maybe some radioactivity or something like that. Another is noise, where for which is kind of typical that the measured values have significantly higher variance than usual. And there are many other types of errors, like the calibration error, when, for example, you deploy a sensors, the initial conditions change in time, and then the sensor has, for example, offset or some kind of relation, or maybe cosine relation, doesn't have to be linear at all, but you can still get the data from such a measurements, because there is a known, or not known, but constant in time relation between the real data and the measurements. So I was focusing on these three types on top. And I was looking for different approaches nowadays used, and I have focused in this presentation on 4 groups, which I have divided the methods into. First is heuristic-based methods, which are still probably the most used methods today. They have their advantages and disadvantages as well. Biggest advantage is that they are easy, and also due to that fact they are fast and they can be done without the computation power. But on the other hand, it's not robust at all, because they are ad hoc solutions for specific measurements, and closer to them. What is important that when we here is that we can calculate the standard deviation or variance of a time series in some sliding window of size n, and from that we can find the previously defined errors. When it's constant, there is 0 variance. So if we have in some window 0 variance, we instantly know that it is the frozen sensor, and we can classify. For noisy sensor, we know that it is higher. It is more difficult to determine what is high variance, so we need to set some threshold. And this is a tricky part, and we will get to it on the next slide. And for short errors, this is the biggest problem, because it might also increase variance, but we will only know that there is some problem, but we won't be able to determine if it is a noisy measurement or there are more short errors. So what can we do? We can use some additional knowledge of the measuring process. For example, we know the maximum. If we have a light sensor, we know the maximum incoming power, and everything above that is strange. We have more sensors, but this is not interesting for us because it's not robust at all. We will each time have to choose the threshold. So how can we automatize it a bit? We can create a histogram of variances for whole time series. Like we can calculate not standard deviation, but the each deviation, where the xt minus this is what we are interested in, and we create a histogram of all of them, and we can use it as a probability function. For example, the histogram will look like that, and we can calculate the confidence interval on it as well, and we can say that the variances inside the confidence interval will be okay, and here we have first and second threshold. So we can basically automatically determine what is the variance threshold for us. And in case of short errors, we can create something called rate of change when we calculate a new time series where we have, for example, ratio between the successive values, and we can create a histogram from the rate of change, and again calculate the confidence interval and set the threshold for that as well. So this is very easy. In practice, it works really good to determine some interesting values, but how I said, it's more ad hoc. What else we can do? We can, use correlation-based method, which has the assumption that the observed phenomena is detected by multiple sensors, so that there should be a correlation between the values from each sensor, which can give us the ability to create a prediction based on the data from different sensors and compare it with our measurement from the examined sensor. And if the difference is again higher than some set threshold, we can mark the measurement as probably faulty or interesting. So how can we predict the value? Here I have the easiest possible example where we have two sensors. One is marked T1 and T2, and we can see that the prediction is based as a difference from mean value, and it's multiplied by the basically correlation of these two sensors, these covariance divided by variance. So if we know, and we can from some training set calculate the value of variance of each node of each sensor, and we can also calculate the covariance. We can make an easy prediction model which will model the future behavior, and we can compare, we can use it, and again there is a problem that we have to set the threshold. So probably if we have more nodes, we can calculate on them the threshold. We can use some optimization techniques, but this is the tricky part, like always setting the threshold. And that's for the, but sometimes we don't have multiple sensors and we are interested in finding out the unsuspicious values just from the time series of the one sensor. So again, there is many approaches how to model time series. For me, it was most interesting was autoregressive moving average, and okay. So, what are the goals of identifying analyzing the time series? So, first we want to fit the model to maybe even better understand the phenomena itself, if we can fit some model in it, and also, as before, to predict the value, so we can compare the real measurement with the predicted value, and the principle is again the same, and if it is significantly different, then mark it as suspicious. So the measurement we can model as a value, which is, how you can see there, some kind of systematic part which we can predict, and in addition to that there is a random error, which is usually modeled, which is called, or usually modeled by white noise, which is sampled from standard normal distribution with zero mean value. But the systematic pattern, again, we can usually divide into the trend part and the seasonality, which is periodical and periodically repeats with approximately same period. We will see it on an example data set. Here, the data set over there is well known. It's the number of flight passengers in 12 years. You can see that there is a change during the season each year, and that remains relatively same. It is the seasonality, and there is a trend where the total number of travelers increases. So what can we do? We can analyze like each part of the systematic pattern separately. So how can we analyze the trend? First of all, it's good for us when we can smooth the function, like remove the seasonality here is the goal. And for smoothing, we can use moving average, but it's not the moving average from this, it's just the same name, but it's not the moving average model. We will get to it later. So we will have some window sliding over the data and doing some local averaging. Or we can use a median, it depends on us. After we have a smoothed curve, which in this case might look much more like this, we can fit a curve to it using some kind of, for example, least squares methods. And then we here is written that we can use a linear least squares, but then before that transform it with logarithmic exponential and so on. Normally there are packages for non-linear least squares as well. But after that we have a pretty good image of a trend in our data set. But what about seasonality? Seasonality is defined as a correlation dependency of order of given order, which means that if we have a data set, we have a correlation between Tn and Tn minus k, where k is the order. So how can we find it? And here is important to here can help us to create a correlogram, so-called, which is a plot where we calculate the autocorrelation for different orders, for different cases, which are in terminology of time series modulation called lags. We will have on next slide the example of such a correlogram, and of course the formulas for autocorrelation. It's basically what we have taught in statistics here. It's covariance divided by variance, and this is the example of correlogram. And from the shape of correlogram, we can determine which kind of model would fit the best for our time series, so we can predict it. Because now we have a pretty good idea about the trend and seasonality, and now we want to predict the next value or series of values, so we can compare it with real measurements, and we can conclude if they are somehow interesting. So the picture on the right hand side, it's a partial autocorrelation function, the result, which means partial autocorrelogram, and this is nothing else than conditioned correlation. We have correlation, how it's written there. It's covariance. And if we in this regressive model, which we use, have like more values on which the next can depend. For example, if we want to do the correlogram of order 3, then the values, we will get on the next slides to the part where we can model the data and how autoregressive models are used, and this is something for it. So if we have free autocorrelation, then the value here depends also on xk minus 1 and xk minus 2, xk 2. This is one. So we have to consider it, and we calculate covariance of conditional xk sines. So this is the formula, but again we have ready functions for that which can do it for us. And if we have a correlogram and a partial correlogram, we can determine which model can fit it the best. But first we will have a look on the models themselves. Probably I made the wrong order of slides. I should have put this before. So autoregression has a parameter p, and this p means the order. And basically it is that the next value you can calculate based on the p previous values from the time series. It is written there. There is some constant. It usually is 0 because it's transformed into the difference from the mean. Because all these models has has a request for stationarity, which means that they have a constant variance and mean value in time. So, only thing we need is to have these parameters, and they and if you want to model stationary time series, then we need some kind of restriction on these parameters as well, because this model is stationary only. I don't know if I have written, if I have on my slides the condition. I can show you. No, they're with this maybe. Okay, so the condition is that when we take the parameters and we create a polynomial, this polynomial has to have all its roots in a unit circle in complex numbers, which means that this is the condition, but again, it's not so interesting for us. We can. Oh no. Not going into details. It's just a research. This is the condition, and we can. I didn't have the MA. Oh, here. Sorry. Moving average filter. It's another approach. The previous one was that the data is based on the previous values, and moving average calculates the data from the error part, from previous errors. But problem here is that they are not measurable, because you have a measurement, and this is a combination of some kind of systematic part which you are trying to model here, and the error. But you have only the addition of these two. You have no idea how they are. How they are like divided, which part is the error and which part is statistical. So it's much harder to use it, easy to calculate the next value. So in these models, usually autoregressive predictions are used, even if we have a combination of both, which is called autoregressive moving average. And how you can see it over there, basically it's just the combination of these two formulas put together, and in practice it is implemented in many programming languages, and finding these phi and C parameters isn't easy, but all the software do it for us, and only thing which we need to do is to find out the parameters which are the number of moving average parameters, number of autoregressive parameters, and which are the orders of autoregressive and moving average models. And that we can do from the parallelograms and partial parallelograms I have shown you. It is on this slide. If you take, for example, you can see that if the shape of parallelogram is exponentially declining, and the autoparallelogram will show us the order of autoregressive model which we will use. And if you look at this data, we can probably say that this is exponentially going to zero, so we might be able to use the autoregressive model, but we can be sure because we have only few lags there, so we can be sure, and from that we would probably determine that it has no significant decrease, which would lead us to the point that it is not stationary, which is true in this case because there is obviously a trend in the data. So what I have said, that it is important for us to use their packages for autoregressive moving average almost in every language we have. In Python, I was looking in MATLAB and I found something in R. I didn't try it, but I'm planning to because I'm interested in it. So what we have to do is to visualize the data, realize if they are stationary or not, then make them stationary, which are again two basic approaches how to do that. In this model, ARMA, and there is also a version ARIMA, where E means integrated, which makes the data stationary first by differencing them d times, and d is again the parameter. This is one approach, and probably more interesting is when we have an analysis of a trend, how I have shown before. We can fit the curve of a trend to the data, then subtract it from whole the time series, and we for sure have a stationary data. We can use the ARMA model by finding the parameters from creating a correlogram and a partial correlogram, and so find the best fitting model, if autoregressive moving average combination or so, and find the orders, the parameters P and Q, and then like make the software do the magic. So it's not so hard. Hard is only the part behind. Okay, so this is for the probably time series based on autoregression and moving average filters. And the third, the last class of methods is learning based. Again, there is so many approaches you can use. Genetic algorithms and so many approaches, and I have focused on hidden Markov models here, and then there is some kind of method which is like out of all categories, which can only not predict the values, and it's not complex, but it can give us a good clue only if the sensor is faulty or interesting to us. And this will be at the end, and I've put it in learning-based methods. So, hidden Markov models, it's, you all probably know it. It is very similar to the Bayesian network we had here, because it's, it leads to dynamic Bayesian networks. So we have some set of a state where some of them are marked as errors, and we have a transition function which defines us the probabilities with which we will transform from each state to another. And we also have some inputs from the model, and these are the measurements we have. And for each state we can calculate the probability of the measurement we get, and again set some threshold if it is interesting for us or not. There is a really nice Bayesian network based on Markov chains. We have these outputs, log, shock, and clean, and let's say that it is we had a good good presentation on that. I won't go into the details, but let's say that it is rainy and next measurement is fog, and we have to calculate the probability of the measurement. And here it is more complex because we have to summarize it even through all the ways how we could get there from the start. So again, we have to set the number of steps we are interested in, and then simply say that we were in some state, like let's say 5 states back. We will say that we were in there with 100% because we have to calculate all the way to the beginning, which leads us to infinite row. But we can calculate the probability of the value based on the fact where we were and how could we get there, like some of all the possible paths. And if this is really like not probable, then we will say that it's probably faulty measurement. And the last approach was something based on cross-validation. It was like more idea. It was more my idea, and then I tried to find it in some articles because I'm not sure. I couldn't find any good results. Some people have used it, but there weren't results. It was just mentioned as alternative. But I'm interested in trying this. We have a sensor and like hold a set of sensors, and we can calculate some kind of statistic vector. Let's say standard deviation, variance, confidence interval. If we can create a histogram of these differences, whatever. And then we remove one sensor from that data set and calculate it again. And if it if it gets better, then probably the sensor was bad, was really noisy. We can determine the noise there. But on the other hand, it's not good for detecting these constant errors because it will get worse actually. Because it depends on our feature vector, on our features which we will measure. But it's very easy, and it might find the most noises or with totally different mean value, and this is what we are probably interested in. And I think that this is